Hi, I'm Derek Hartman, an applications engineer from Analog Devices. Today I'd like to talk to you about a circuit from the lab note CN0191. I will start with some work on the whiteboard to explain an outline of the circuit, and then I'll move to the lab for some bench results. The CN0191 provides a 20-bit plus minus 10 volt voltage output, achieving plus minus 1 LSB INL and DNL. The circuit components have been chosen to provide the highest output of performance. All the design files, documentation, and even the hardware are available from analog.com. The heart of the circuit is a 20-bit DAC, the AD5791, which features guaranteed plus minus 1 LSB INL and DNL performance. The output is not buffered, so we will buffer the output using the amplifier AD8675. The reason this was chosen is for its low noise, 2.8 nanovolts per root hertz, low offset, 75 microvolts, and also for its 10 megahertz bandwidth, so we can achieve a high system throughput. The other things to note are, as the AD5791 is a voltage mode R2R DAC, there is no need for a feedback resistor which would act as a noise gain element in the system. Then, the reference inputs of the AD5791 also need to be buffered to provide the dynamic load required by the AD5791. The amplifiers chosen are the AD8676, which are in fact the dual version of the AD8675. Another feature of the AD5791 is that the reference inputs can be forced and sensed. The advantage of this is you can compensate for the parasitics inside the AD5791 and achieve the very high plus minus 1 LSB INL and DNL accuracy. Another thing to note that this whole circuit is in fact the circuit used in factory test to guarantee the INL and DNL performance of the AD5791. The last thing needed is to actually apply a reference voltage. Typically, you would start with some unipolar reference. In our case, we have chosen a 5 volt precision reference source. This will need to be gained up to the plus minus 10 volts required by the DAC. The amplifiers chosen for these gain elements are the AD8676. These were chosen again for the low noise, 2.8 nanovolts per root hertz, and low offset, 75 microvolts. This amplifier here will operate in non-inverting mode to gain up the 5 volt reference to plus 10 volts. This amplifier here will act in inverting mode to gain up the reference to minus 10 volts. I shall mention that this reference could be any value as long as these resistors are scaled accordingly. The high precision and accuracy provided by the circuit could be crucial for medical applications, precision test and measurement, as well as precision industrial controls. So in summary, the circuit is providing a plus minus 1 LSB INL and DNL performance. It is also providing a low noise voltage output. And these are all achieved at the 20-bit level. Now I'd like to move to the lab for some bench results. So here is the CN0191 hardware. Specifically, here is the AD5791 20-bit DAC. Also, here are the amplifiers we talked about earlier, the AD8675 and the AD8676. Also, I'll mention the scaling resistors. On this board we are using 0.1% 5 ppm resistors. This will introduce some gain error into the system, so if desired, Instead, 0.01%, 0.6 ppm per degree Celsius could be used, or something even more accurate. I should also mention that the layout of this circuit is optimized for DC accuracy and performance. The reference input is connected to the Kronheit Model 523 precision source and calibrator, which is outputting a precision 5 volts, which is very stable and low noise. The output of our CN0191 is connected to an Agilent 3458A 8.5 digit precision multimeter. This allows us to look at the 20-bit performance provided by our circuit. Our supplies are plus minus 15 volt supplies, which supply both the DAC and the amplifiers on the board and are amply decoupled in the layout. Lastly, we have the SDP communicator board, which is connecting this board to the PC software. So the first test we shall perform is to output a DC voltage. The first voltage we'll output is 5 volts. Again, I've calibrated the gain errors earlier to account for the resistor errors. As you can see on the multimeter, our output is 5 volts plus and minus a few microvolts. I shall mention at the 20-bit level for a plus minus 10 volt output, 19 microvolts would be 1 LSB. I shall now output a second voltage, minus 5 volts. And you can see here again, the output voltage is minus 5 volts, plus and minus a few microvolts. Then we shall move on to an INL measurement. And I shall start this measurement. Here I am performing an INL measurement over 1,000 codes. It is possible using the software to measure the INL from code 0 to code 2 to the 20, though this would take a long time. It is also possible in the software to specify any other range or any code step to perform the INL measurement with. After the samples are acquired, we can see our INL plot here on the screen. And as you can see, this is fitting well within our plus minus 1 LSB specification. In fact, as you can see on this screen capture, it's 0.3 LSB to minus 0.2 LSB. So the next measurement we shall do is a noise measurement. I shall start this measurement now. This measurement is performed over a 10-second period. The Agilent meter is set to a slow data rate. This acts as a low-pass filter effectively. So the result should be a noise measurement roughly in the 0.1 to 10 Hertz band. When the measurement is complete, the software gives us the option to save the data to a file, which I shall do here. And here's our noise results. As you can see, the noise level is roughly plus 800 nanovolts to roughly minus 700 nanovolts. So you can see in this 0.1 to 10 Hertz roughly noise band, there's very low noise level. So in conclusion, the CN0191 provides a system-ready solution to implement a precision 1 ppm INL and DNL 20-bit voltage output. This could be used in precision medical, test and measurement, or industrial automation applications. For more information, please visit www.analog.com/CN0191, or for more information on any of the circuits from the lab available, please visit www.analog.com/circuits. Thank you very much.